Department of Electrical and Electronics Engineering at Bilkent University. This seminar that we are hosting today is special because it's being sponsored by the IEEE SPS Turkey chapter. Our speaker is Dr. Hiroshi Sawada from NTT Communication Science Laboratories. Let me briefly introduce him to the university, this audience. Dr. Sawada received his BE, ME, and PhD degrees in information science from Kyoto University. He then joined NTT Corporation, and he has been a member of the corporation for a long time, where he's currently a senior distinguished researcher in the communication science labs. His research interests include statistical signal processing, audio source separation, array signal processing, and latent variable models, along with optimization and computer architecture. He has served as editor in numerous journals that IEEE publishes, including TASLP and Open Journal of Signal Processing. He's a member of the Audio and Acoustic Signal Processing Technical Committee for IEEE. And he has been named a distinguished lecturer of IEEE SPS in 2022. He's an IEEE Fellow, IEEE Fellow, and a member of ASG. The title of his talk today is Blind Source Separation of Audio Signals by Simultaneous Estimation of Individual Sources and Linear Transformations. And without further ado, I would like to thank him for accepting the invitation to be here today and give the word to him.
Thank you for the kind introduction, and thank you for everyone coming to my talk. And I will now share my screen. Okay, is it okay? Everyone can see my slide?
No, not now.
No. Let me try again.
Yeah.
Okay. Okay, thank you. So let me start my talk. So today I will be talking about blind source separation of audio signals. And this is the outline of my today's talk. And in the first part, I will introduce what is blind source separation with a demonstration of audio blind source separation. Then in the second part, I will talk about the details of independent component analysis, ICA, which estimates a linear transformation to separate mixed signals. And in the third part, I will be talking about non-negative matrix factorization, NMF, that models a source signal by a low rank approximation. And in the last section, I will introduce independent low rank matrix analysis, ILMA. It is a sophisticated integration of NMF and ICA for simultaneous estimation of individual sources and linear transformations, and achieves BSS, blind source separation of audio sources mixed in a real room environment. So, is anyone speaking, or may I continue? Okay, yeah, let me continue. So blind source separation, BSS, is a task of separating mixtures into individual sources with no or very little prior information on sources and no information on how they are mixed. As shown in these references, BSS has been studied for more than 30 years. And independent component analysis, ICA, is a primary method for BSS and shares almost the same history as BSS. ICA can be applied to various signal processing applications, including images, biomedical signals, and audio signals. I recognize that today in in today's audience, there are many image processing researchers. So I have some image examples in my talk, but the main topic is on audio signals, as I have been working for more than 20 years. So this slide shows a very simple BSS example for image mixtures. On the left, there are two source images, a boot and a shirt. And these are mixed with these four coefficients to make the mixtures in the middle. Then the task of BSS is to separate these two boot and shirt mixtures into individual sources with no information on the sources and the mixing system here. So ICA is applied to these mixtures and then estimate these four coefficients W to make the outputs mutually independent and eventually can separate the mixtures. So this is a simple BSS example for image. And today's talk is mainly for speech and music, but the structure of the BSS is almost the same as the image example. Namely, we have two sources or several sources, and they are mixed. And then we have several mixtures as observations, and we are trying to separate them by linear transformation. And we should separate the mixtures without the information on sources and the mixing system. BSS for audio signals has also many applications, like, for example, a cocktail party effect. It is a human's ability to separate or focus on a single conversation, even in such a kind of very noisy environment where many people are talking. And we want to implement such an ability into a computer. For speech recognition, if we can extract target speech from the background noise, the accuracy of speech recognition increases. And for music analysis, if you want to... Okay, does anyone speak, or may I continue? Okay. So if you can separate each instrumental sound from an orchestral play, it will help music analysis or your practice if you play an instrumental part. Okay, this slide shows there are various BSS methods for audio. The horizontal axis of this table concerns the number of source N and the number of microphones or sensors M, the relationship between these two numbers. And the vertical axis concerns whether we utilize training data or not. ICA is placed here for determining the situation as a basic or primary method for BSS. NMF, non-negative matrix factorization, is basically for single channel case, but we can extend NMF to multi-channel case, and especially ILMA is a combination of NMF and ICA as the final method which I will talk today. And of course, there are much more other methods like shown in this table with gray in gray. And I will not go into the detail of these grave methods, but please ask questions if you are interested in. Okay, now I want to do some BSS demonstration. And if we are together in a lecture room, I mean, if I will be in Turkey, I want to make a live demonstration with you, but today the topic is online. So instead, please watch a video playback where I recorded simultaneous two speeches by this IC recorder equipped with two microphones. So please watch the video. Hi, from now, we are going to record speech mixtures with this IC recorder equipped with two microphones, here and here. So let's start. 3, 2, 1.
We are demonstrating blind source separation for convoluted mixtures of speech in a real room with real talkers.
Thank you. Okay, so video and audio is okay for you? Fine. Oh, okay, thank you. So now I have the record of mixed speech, and I will play the recorded sound like this.
We are demonstrating blind source separation for convoluted mixtures of speech in a real room with real talkers.
So in the demonstration, I will copy this file to the PC, and now I already have it on PC. And then I will run my BSS program to separate the mixture. Okay, let me run my program here. And now the BSS program finished. And I have separated signal here. So let me play the first one.
USIPCO is the flagship conference of EuroTIP, addressing all the latest development in signal processing.
So men's voice are extracted, separated. And on the second channel,
we are demonstrating blind source separation for convoluted mixtures of speech in a real room with real talkers.
This is the woman's voice, but maybe you can hear some residual interferences of the man's voice. So I would have to say that the separation is not so perfect, but you can get the idea of blind source separation. So I hope some idea. Okay. So let me continue. Okay. So this was the introduction of blind source separation, and then in the second part, now as a second part, I will go into the details of ICA. So I have to mention that in ICA or BSS system, both mixing and source separation systems are linear transformations, as shown in this figure. So we have vectors, two-dimensional vectors here and here and here, and the 2x2 matrix in this case here. So the situation can be represented by vectors and the matrix and their multiplications. So that's why I'm saying that we estimate a linear transformation in ICA. Okay. And please remember that sources are denoted by S, and mixtures are by X, and the separated signals are by Y. So independent component analysis estimates a linear transformation W here we call this separation matrix. It is without information on sources and the mixing system. And how we can do that? It is by assuming the sources are independent of each other and making the output Y independent of each other. And in addition to the independence, we need to further assume that source distributions are different from Gaussian distribution or normal distribution, and making the distributions of the output far from the Gaussian. So this is the additional requirement for ICA. So from now, I will spend 10 minutes or so to explain why do we need to assume that sources are far from Gaussian, and also the way how to make the output, IC output far from Gaussian. In the why part, I will examine the statistical properties of sources and mixtures, and also statistics quantified by entropy. And in the how part, I will assume the source model and derive the ICA cost function and also the ICA algorithm. So let's start with the why part. This slide shows the statistical property of a source of sources. Now I have a single source here. Please listen to this speech source.
The historical film moved her deeply. Canada was established only.
So it is English man's voice. Did you hear the sound? Okay. So, and this is the waveform, time domain waveform of this sound. And from this time domain signal, we can build up the histogram of this signal shown on the right. So to make a histogram, for example, for this green sample here, this sample's amplitude is almost 0. So I put a boat on the 0 here on the histogram. And for another sample here, purple sample, which is around -4, so I put a boat for -4 here in the histogram, and so on. And we can do the same thing for all the time, and we can build such a histogram. Now, I'd like to ask someone in the audience, what is the characteristics of this histogram? Does anyone have something to say for this histogram? Would someone please ask?
Someone said
Answer.
Chat box similar to impulse.
Oh, yeah, thank you. You mean around the 0 amplitude, the histogram is really high. Okay.
It looks like a Laplacian distribution.
Oh, yeah. I will be talking about Laplace distribution later, and yeah, you are quite right. Okay, thank you. Thank you for answering. So yeah, as answered, it is similar to Laplace distribution, and it has a very large high peak on around 0. So please remember this specific characteristics. And now, I would like to examine the statistical property of mixtures. And in these cases, I made mixtures simply by mixing n speech sources and then normalizing their variances to 1. And the number n, the number of sources n was varied 2, 8, and 16. And this slide shows n is equal to 2. And please listen to the sound when the number of sources is 2.
The
Many
historical
expensive
film
houses
moved her
surrounded by
deeply.
gardens.
Canada
There's
was
such a
established
suspicion of-
only.
So for such mixtures, we want to separate the sources. And we can build up the histogram for the n equal 2 cases, like shown in the rightmost figure. And we can continue for example 8 and 16. Please listen to the sound. This is the 8th case. And this is the 16th case. So in the 16th case, it sounds like almost a noise. Okay, and of course, we can build up the histograms for the 8th case and the 16 cases. And as you can see here, as n increases, the histogram approaches the red curve. So from left, the number 1, and to the right, number 16, the histogram approaches the red curve. And again here, I'd like to ask the audience, so what is this red curve? Someone recognize this shape, the shape of this red curve?
So in the chat box, they are saying Gaussian.
Yes, thank you. So this red curve is the distribution of the Gaussian. And this slide states the central limit theorem. Okay, thank you. Someone also write in the chat. So central limit theorem states that even if the original sources are not Gaussian, the mixture of them tends to be Gaussian as the number n of sources increases. This kind of means that Gaussian distribution is the most random distribution, and actually it has the maximum entropy among any distributions with the same variance. So I examined the entropy of these sources and mixtures by myself, and entropies are shown in this table. So as you see, the entropy increases as the number of sources increases and approach to the entropies of Gaussian here. So this is just the verification of central limit theorem by myself. So this is the end of why part. And now I'm going to going into the how part, how to make the RC outputs independent and far from the Gaussian distribution. So based on the discussion so far, one way is to estimate or guess some separation matrix W, these coefficients, and produces some outputs and check the entropy of these outputs are decreased or not, or just picking the minimum entropy output is one way. However, entropy calculation is kind of cumbersome, so this way is not so practical. Instead, a practical way is by assuming the source model or distribution. This allows us to calculate the entropy approximately and easily, and also to employ maximum likelihood estimation. So let's discuss the source model. Generalized Gaussian distribution shown here is very convenient because it can represent various distributions by changing the hyperparameter beta. The Gaussian distribution corresponds that beta is equal to 2 here. And if we want to model sub-Gaussian distribution, we can set larger beta. For example, beta is equal to 4. And in this case, the distribution shape looks like this green curve. So it's like a uniform distribution. And this kind of distribution represents images and also signals for wireless communication. On the other hand, to model audio signals, we select beta is equal to 1, which corresponds to the Laplace distribution, which someone in the audience already mentioned. And the shape of Laplace distribution is this blue line here. So in this sense, this generalized Gaussian distribution is very convenient. And in this talk, we are talking about audio signals. So please remember the Laplace distribution. And I'm continuing the modeling audio source. So in the previous slide, I already showed the Laplace distribution here. However, there are two typical choices, and the other choices is time-varying Gaussian distribution shown on the right. In any case, the distribution looks like this kind of peaky shape. And I want to employ the second one, the time-varying Gaussian distribution, in this talk because it fits nicely with the NMF model discussed later. So let me explain what it is. So time-varying Gaussian distribution has time-varying variances. For example, for time 1, and the n is source index. For time 1 here, the variance is 4, which is relatively large variance. So I sampled the signal here and got a large positive amplitude here. And for the second time slot, the variance is, for example, 1, which is rather small. So the sample was almost 0 here. And we can continue and so on. So by changing the variance by time, the shape is not the ordinary Gaussian. So I mean, the total statistics here does not look like Gaussian, and it is rather similar to Laplace or super Gaussian distribution. Okay. And this slide shows by employing Laplace distribution or time-varying distribution, we can approximately calculate the entropies. And I actually calculate the entropies approximately here. As you can see, by comparing the second law and the third law or the fourth law, the approximation is not very accurate. But the important point is that in any approximation cases, the entropy or approximated numbers are increasing as the number of sources increasing. And these numbers are minimum when the number of source is just 1, as you can see in these red numbers. So this means that we can employ these distributions to approximate the entropies and also to model the sources in the context of ICA. Okay, so let me derive the ICA cost function. I'd like to start from the negative log likelihood here which should be minimized in the maximum likelihood estimation, given the observed mixtures from time 1 to time j. And then I have 4 assumptions here. The first one is sample independence, which makes the derivation very simple. The second one is linear operation, like here. So this is basically the system model of BSS and ICA. And the probability distributions for the mixture X and the output Y are connected with this equation. And the third assumption is output independence, which ICA would like to solve. And the fourth assumption is about source model, which is the time-varying Gaussian I employed for the purpose to connect this topic and the NMF. And the distribution equation looks like here. So it is like complex valued Gaussian distribution, but we have time-varying variance here, H, which is indexed by N, source index, and also J, the time index. And as I explained in the previous slide, time-varying Gaussian distribution looks like in this figure. So putting these 4 assumptions into the negative log likelihood, I have this specific form of the ICA cost function shown in the bottom, where I have time-varying variance parameter H newly, although the main purpose of the ICA is to estimate this separation matrix W. Okay, so this is the cost function we would like to minimize in the context of ICA. And there's an ICA algorithm which is called iterative projection. It is particularly efficient for the specific cost function based on the time-varying Gaussian distribution. So I will send you this slide maybe after this talk. So please ignore the detailed part. But please understand the abstract structure. On the left, we are updating separation matrix W by these equations or updates. And on the right, we update the variance, time-varying variance parameters H, simply by taking the square power of the output Y plus some positive small numbers. And we can iterate these 2 updates until convergence. And this slide shows a simple example of the ICA algorithm execution. And in this case, I synthetically made the time-varying Gaussian sources and mixed them with this mixing matrix. And I have the mixtures here, starting from the 0th iteration. And by iterating 10 or so, we get this separated signal on the right bottom. And this figure on the upper right shows the situation of convergence. So the y-axis is the cost function, is rapidly decreasing as iterations goes on. So I can say that the algorithm is efficient enough. Okay, so this is about the detail of the ICA. Now, let me go into the non-negative matrix factorization NMF. Non-negative matrix factorization factorizes a given matrix X into smaller 2 matrices T and V, And there's a restriction that all matrix elements are non-negative. So for given matrix X of size I and J, we need to specify the number of K, the number of bases here, and factorize this X matrix into T and V. And for this specific 4 by 5 matrix, we can get this 4 by 2 and 2 by 5 factored matrices. And please focus on these 1, 1, 0, 0 column vector here. There are 2 such column vectors in the input matrix. And this 1, 1, 0, 0 vector appears on the T matrix, T factors matrix. This means that NMF kind of perform clustering or frequent pattern extraction. Okay. NMF has many applications, including image processing, document clustering and analysis, recommender systems, and audio processing. And in this talk, I'm talking about audio processing, where we want a data format of matrix. So to make this matrix, we apply short time Fourier transformation, STFT, to the time domain audio signal, and to get this kind of time frequency domain signals, which is called the spectrogram. So this time frequency domain signal is a data format of matrix, so we can apply NMF to this spectrogram. This slide shows the NMF applied to an instrumental sound. So please listen to the sound here. So for this sound, I applied NMF with 5 bases, and we got this T and B matrices. The T matrix represents extracted sound patterns, and V represents the timing of when each sound is activated and then attenuated along the time. So we can play with synthesizing only 3 sound patterns by taking only the purple part. And please listen to the extracted sound. You may hear the 4th and 5th bases are eliminated in this synthesized sound. Please listen again. Okay, and NMF can be applied to a more realistic music excerpt. So please listen to this music excerpt. And I applied NMF with 10 bases, and this time NMF has been extended to have a time axis in the T matrix. So I mean, T matrix have time width. This is to capture the sound patterns that last longer than the STFT analysis window. And so I have 10 bases, and for example, I can play only the second base like this. So I guess this second base, it is hard to recognize this second base in the original music excerpt. So NMF do the kind of blind source separation. Okay, so from now on, let me spend 3 slides to explain the mathematical aspects and also algorithmic aspects of NMF. So the aim of NMF is to minimize the matrix divergence uppercase D between X, the given matrix, and H, the product of T and V. And the matrix divergence D is the sum of the element divergence lowercase d here. So for this element xij, we need to calculate hij here, which is the inner product of T and V matrix, T vectors, corresponding T and V vectors. And we compare these two elements, and we want to minimize the divergence between these elements in the whole matrix sense. And there are 3 well-known element divergences shown here: the squared Euclidean distance, and also Halbach-Leibler divergence, and also Itakura-Saito divergence. And in this talk, I employ Itakura-Saito divergence because the origin of this divergence is the time-varying Gaussian distribution. Okay, so we have matrix divergence here and element-wise Itakura-Saito divergence here. So to build up the NMF cost function, I simply substitute this element-wise divergence here and eliminating constant terms. Then I get this NMF cost function shown in the bottom here. So this is very simple form. And this NMF cost function can be effectively minimized by the well-known multiplicate update rules, which iterates these 4 operations until convergence. A nice thing about this update rule is that once T and V are initialized with non-negative values, the update rules keep them non-negative. So we don't have to care about whether the non-negativity is satisfied or not after every update. Okay, this slide shows an example, NMF example applied to the mixture of drum and the guitar. So please listen to the sound. So I applied NMF to this single channel mixture and obtained 10 bases on the right. But to separate this drum and guitar, we need to solve a kind of clustering problem, meaning that which base corresponds to which source. So I listened to every bases by myself, and I solved this kind of clustering technique, clustering problem by myself, and I got these 2 separated results. So this was the drum, and So actually it works, but it is by labor intensive. I think it is difficult to make this automatically. So now I want to go into the detail of ILMA, which integrates NMF and ICA and achieves BSS of audio sources mixed in a real room environment. So with this slide, let me explain the difficulty of real room audio BSS. In a real room environment, audio sources are mixed through the process with delay and reverberation. This is much more difficult than single ICA with scalar coefficients shown here. And a typical approach to real room audio BSS is again by applying STFT, short time Fourier transform, to get time frequency domain signals called spectrogram. And for this spectrogram, we apply multiple ICAs, where each ICA corresponds to each frequency bins. However, there's a problem called permutation problem in multiple ICAs. Let me explain this. A single ICA solution has permutation indeterminacy. So in this case, I have men's voice on the first output and the women's voice on the second output. But swapping them is again an ICA solution. So there's a permutation indeterminacy in ICA. And for multiple ICAs, there's a specific problem. So in this image example, so in this case, images are divided into 4 regions. And I applied 4 ICAs here to get these separations. And actually, in this case, the permutation problem occurred because on the first channel, on the first region, I have short, but the other region, I have boot images. So I need to swap this short and boot on the first region to get the proper separation in a whole image sense. In the case of audio, the situation looks like this. And if we get just raw ICA output, it sounds like this. Oh, let me play this sound.
Many of the caves on the study are occupied.
So, I mean, the sounds are still mixed, even if the sounds are separated in each frequency bin. So I need to align the permutation, and I got this kind of separation. Oh, let me play. It is difficult to. Okay.
Many of the caves under study are occupied.
Okay. So let me discuss that ICA and NMF complement each other. So for single channel ICA, it separates mixtures with multi-channel setting. And for single channel NMF, it models a source by identifying frequent sound patterns. And now I want to extend ICA to multiple cases, but in this case, I need to solve the permutation problem. But NMF can help by modeling a source for this permutation problem. And also, I want to do some source separation only with NMF, but for a mixture of sources, I need to solve the clustering problem, which I mentioned earlier. But ICA can help with this multi-channel setting for the clustering problem. So we integrate ICA and NMF So let's integrate ICA and NMF, and let me explain this. So starting from the mixtures of piano and violin, so I first apply ICA to get these output. But this output is still mixed because of the permutation indeterminacy. Then I apply NMF to each output to get factored matrices T and V for each output. And then I calculate the product of T and V to get H matrix, and this H matrices are fed back into the ICA part as a time-varying variance parameters of the time-varying Gaussian distribution. Then I can continue this iteration until we get the separated output on the ICA output, and also row rank matrices on the NMF output. And these two row rank matrices are independent. So we named this method IRMA, independent row rank matrix analysis. Let me spend 3 slides from here to explain the mathematical and algorithmic part of IRMA. We can say that IRMA is the combination of multiple ICA and multiple NMF, and the number of ICA is the number of frequency bins, and the number of NMF is the number of sources. Here we have I multiple ICAs for all frequency bins, and on the right we have NMF for all sources. And from the ICA part, separated signal Y fed into the NMF part by calculating the power spectrogram of this separated signal. And from the NMF part, the time-varying Gaussian distribution, the variance parameters of the time-varying Gaussian distribution is fed into the ICA part. This is the cost function of IRMA, and I will not go into the detail, but I will give you the interpretation here. So this red part is for NMF for each sources by changing N index. And this blue part is for ICA cost function for all frequency bins. However, to be exact, the variance parameter H are constrained by the NMF model here. But thanks to this constraint, the permutation problem of multiple ICAs is solved. This slide shows the IRMA algorithm. This is very similar to the ICA algorithm as we shown, as you see in the previous slide. And on the left, we update separation matrix W, and on the right, we update the time-varying variance. But this part, this red part, is replaced by the NMF algorithm. This slide shows a BSS example for music mixtures solved by IRMA. And as shown in this figure, there are 2 microphones in this case, and we have guitar and drum sources. Please listen the mixtures. And we applied IRMA, and the algorithm converged with 100 iterations as shown in this figure. And we obtained 2 separated signals here. so second separated signal is not so very good, but oh, okay. And so I mean, thanks to the multi-channel setting, NMF can the NMF result is clustered automatically. Okay, so in this case, NMF model the sources like these spectrograms, and ICA estimated the mixing situation. And to visualize this, let me here plot the estimated source directions. This can be calculated from the separation matrix W. And we can recognize that the blue source is coming from around 70 degree, and also green sources are coming from 150 degree, which corresponds to the situation shown on the right. Okay, so let me conclude my talk. Today, I'll be talking about the final goal of this today's topic is real room BSS for audio mixtures. And to solve this problem, ICA and NMF are combined to obtain the ELMA method, which solves the permutation problem of multiple ICA by sharing the time varying variance of the time varying Gaussian distribution. So thank you for your attention, and I'm very happy to answer some questions.
So thank you for the kind presentation. Now we can take questions from the audience. You can unmute yourself or type in the chat box. So maybe I could start with a couple of questions of my own. So you mentioned that this resembles the cocktail party problem that humans have to solve. But you know, if I'm attending a party, I don't really know how many people there are or I don't count them. And the number of measurements that I take, you know, maybe the sound analysis would be different, but I have 2 ears, let's say. I use 2 recording devices. How are human beings able to decipher many different voices with only few measurements? Is that a well-studied topic, or can you give any insights?
Yeah, as I show by this figure, so as you said, we have 2 ears. So in this case, M is equals to 2. And to separate like 3 or more sources, this is the underdetermined cases. And we need to rely on another method than ICA. And so which is not explained today. And or maybe we can formulate the cocktail party problem by specifying that the first source is the target sound, and the second source is the all of the background sound. So by simplifying the problem like that, maybe we can apply ICA. But it's maybe it's too much approximation.
Okay.
Yeah, and as a recent progress of this kind of research, of course, again, also in this research topic, DNA methods are very strong, and you can train beforehand human's voice or other background noise, and yeah, to separate the mixtures, even in this kind of very large numbers of sources. Maybe we can do that with DNA, and also with some data.
And I can ask one more. while we're waiting. So in this setup of the blind source separation problem, we kind of assume how many sources there are in the environment. If you don't know precisely how many sources are there, I mean, how many independent components are we supposed to select? Is there a method to do that selection automatically?
Yeah, that's again a very hard problem. And as I explained, simplifying the source number, like only the first source is here, and the second source is all of the other sources is one way. And another one is like maybe by using 8 microphones, we may separate 8 sources, and but in these 8 sources, we may have a very clear source and also very vague source, which is kind of background noise sources. And if we can evaluate or order the output, then maybe we can pick up the most clear source and then the second most clear source and so on. Then we can select important sources among 8 outputs. So that's the another way. And of course, there are many ways to be studied further. Again, that's very difficult problem. So shall I answer your question? Did I? Yeah.
Yeah, thank you.
Yeah, thank you.
Thank you, Dr. Sawada. I also have a quick question about the degradation that you assume in the beginning, like linearity and additivity are two assumptions for the mixing model. In case of like nonlinear mixing or channel-wise different types of degradation, how would that contribute or degrade the overall results, especially for the last part? When you introduce the low rank regime, for example, does it help towards that direction?
You mean, so you are talking about the contrast between this simple scalar type mixing system and also impulse type mixing system, or you are talking about non-linear mixing system?
Well, other than just linear mixing, in case you consider like more complex scenarios in real environments, such as nonlinear, noisy, or other types, how robust would the proposed approach would be in that case?
Thank you. Actually, I have no experience for nonlinear mixing system, but I only have this kind of reverberant mixing system. So, of course, this delay and reverberation situation is difficult to solve, but they are still linear. So, that's nice part. But of course, this makes the problem difficult. And I don't have my own experience for the nonlinear ICA or BSS, but I think that there are many research efforts for the nonlinear situation, which is not covered today, of course, but again, maybe DNA-based method is again very effective for this kind of nonlinear system, because if you can identify source characteristic, you can extract the sources from the mixture. Okay. Sorry, I'm not so specialized with nonlinear systems. So maybe that's all for my answer.
Thank you, Dr. Sawada. And my next question would be about the party cocktail problem again. In case if there are like multiple languages in the room, humans are like highly capable of just separating any language, even the number of sources are like high. When you kind of consider such prior information, does this help? Like multiple languages mixed together, is it a simpler problem? Or is there any better way to integrate this information into the overall methods, either NMF part or the ILMA, the one that you proposed?
So you are talking about multiple languages like English and German, French?
Yes,
and,
yes.
Yeah. So yeah, of course, mother language is very easy to separate for human, and foreign language is difficult to separate. So today, I didn't show this presentation, but I have some slides showing some like English and Japanese mixtures, and please listen, and maybe this is good for Japanese or something like that. So language dependency is actually there because you can predict next word if you are familiar with that language. And that prediction is very helpful for human to separate the mixture. Okay, and did I answer?
Yeah. Thank you for the presentation.
Yeah, thank you.
So,
Hocam, can I ask something?
okay, yeah.
Let's assume that we know the characteristic of a source. For example, we have pre-recorded sound, and we know that there are two different sources. How can we use that additional information? We know one source before, and we didn't know the other one, but not exactly that source in that time, but from previous records, for example.
Yeah, thank you. Yes, so if we have some characteristics of the sources, then we can utilize this information like in a similar way that we employ NMF to model the source. So maybe this slide help. So these two spectrograms are estimated after the NMF applied, but if you have prior information like this, then you can use this information directly to produce this one, time varying variance fading into the ICA part. So that accelerates the convergence of ICA and also the solving the permutation problem.
Okay, hocam, thank
you. Yeah. Thank you.
So if there are no other questions currently, so let me thank our speaker, Dr. Sawada, once again for sparing the time to be with us today. And I would like to thank the audience for their participation and IEEE SPS for sponsoring this event.
Thank you.
Thank you.
Thank you, everyone, for coming and